Hello, I'm Joe Kimbrell, and this is the presentation component of my EEL 6509 Wireless Communications final project. Today I'll be talking about smart antenna techniques, and in particular multiple input and multiple output systems. So here's the outline of the presentation. We'll start with an overview of MIMO systems, including the fundamentals, starting with the single input, single output system, moving on to single input, multiple output, and then of course multiple input, single output. Once these fundamentals have been set in place, we'll discuss in more detail MIMO systems. Next, we'll go into simulations where I'll talk about the MATLAB code that was used, and then we'll go through some results of the simulations. Next, we'll look into some current applications and challenges about MIMO, including the Samsung Galaxy S5, MIMO and LTE systems, and a few restrictions and integration issues. Let's get started. So the demand for faster and more robust wireless communications has increased drastically over the last decade. This includes the commercial use, which requires large data transfers, and personal use for mobile phones, which the common person uses for many hours every day for various streaming interfaces. So the traditional single input, single output, or CISO transmission scheme is far too slow. So multiple input, single output offers increased robustness, but really no speed up, as this system is still limited by a single antenna at the receiver node. So how do we increase the speed up while maintaining or improving this robustness? The solution is MIMO. It's another smart antenna technique that stands for multiple input, multiple output. And this maintains MIMO robustness through spatial diversity and increases the data rate through spatial multiplexing. So before we move on, let's consider just a very basic mobile communication system. You have a base station as your transmit node and a mobile device as your receive node. In CISO, there's only one antenna at each node, as represented by the diagram on the right. The capacity of such a system can be described by the Shannon-Hartley theorem, where the capacity is equal to the bandwidth times the log base 2 of 1 plus the signal to noise ratio. Now, CISO is by no means perfect. It suffers from multipath effects and works best in line of sight conditions. But in the real world, the transmitted signal can bounce off of solid surfaces, including buildings, vehicles, or natural obstructions like hills. Additionally, as a mobile device moves, the signal takes different paths to the destination and suffers from fading and intermittent reception, reduced data speed, and we need to remember that the data speed is already far too slow. So that's not good. Now some of the benefits of MISO and CMO are that adding multiple antennas at either node reduces multipath effects. In MISO, you have multiple transmit antennas and a single receive antenna, and the receive node receives multiple copies of the data, and these copies take different paths to the destination because they originated from different locations. This is widely used in current mobile communication systems. A CMO with the single transmit antenna and multiple receive antennas behaves similar to MISO. Both of these methods also increase the robustness of the overall system. Now for some of the drawbacks of MISO and CMO. So just like CISO, both of these are data rate limited by their single antenna nodes. So you could have 20 transmit antennas in a MISO system, but that one receive antenna will prevent your data rate from being increased. Additionally, a CMO requires multiple antennas on a mobile device, and on mobile devices, power is a much larger concern than at, say, a base station. Using multiple antennas would result in reduced battery life and potential heat dissipation issues on a fully enclosed platform. So, MIMO, our next step. In a MIMO system, multiple transmit antennas, denoted as M, send data to multiple receive antennas, denoted N, on the same channel. This data is divided into streams and is limited only by the smallest number of antennas. So if you have a 4x2 with 4 transmit antennas and 2 receive antennas, you would have a stream size of 2. Similar, if you have a 3x5, you'd have a stream size of 3. Now, an important thing to note is that sharing the channel leads to all the receive antennas receiving components of all the transmitted stream. So this relationship between receive antennas and the transmit antennas can be modeled as a two-dimensional transmission matrix H. And this provides us a linear equation to calculate the output. The received signal is equal to the transmission matrix times the transmitted signal plus the noise introduced in the channel. The two main components in MIMO systems are spatial diversity and spatial multiplexing. Spatial diversity increases robustness as it sends multiple streams of the copies of the same data. These copies are received at the receiver at different times or at different signal-to-noise ratios due to multipath effects. These differences can be analyzed with smart signal processing algorithms and improve the likelihood of recovering the original signal. On the other hand, spatial multiplexing increases the data rate. So the data rate is split into multiple streams. And the number of streams, as mentioned before, we'll call that M, capital M, is limited by the smaller number of transmit or receive antennas. This is comparable to a cluster of CISO systems, and the capacity equation goes along with this in that it is simply the CISO capacity equation multiplied by the factor M. Okay, so now that we have an idea of the capacity for these different systems of MIMO, MISO, CMO, and CISO, let's look at the simulations and see if we can get a better understanding of how they're all related. So the code I used to run the simulation of the MIMO systems is a special implementation I made of two different MIMO simulators I found online. The first script compared the variable MIMO system to the baseline CISO and allowed you to vary M and N independently. The second script compared several MIMO implementations at once, but was limited to only square transmission matrices, where you have an equal number of transmission and receive antennas. So my custom implementation compares 4 systems at once, and I made a function that takes in M and N vectors so you can vary the size. And this allows you to compare MIMO, both square and non-square, MISO, CMO, and of course the CISO systems. So let's take a look at our first plot. This is a comparison of 3 different square MIMO systems as compared to the baseline CISO. So you can see all 4 increase logarithmically as we expected from the Shannon theorem. And in this case it is quite clear that the MIMO systems increase by a factor M. So for the 2x2 we see is roughly twice as the capacity is twice as large as CISO, and then 3x3 is again 3 times as large, and finally the 4x4 is the best with the 4x increase in capacity. Next we'll look at the comparison between a small MIMO and the most basic MISO and CMO systems. As we expect, the MIMO system outperforms all the other systems at all signal-to-noise ratios, with a capacity increase of 2 times over the baseline. And here we also see that the bottleneck of MISO and CMO systems having 1 antenna at one of the nodes prevents any appreciable increase in capacity, as they both follow the CISO capacity curve quite closely. Next, I have variable MIMO systems, where I have a 4x4 square, and then a 4x2, and finally a 2x4 MIMO implementation. As we mentioned before, there's the bottleneck of the 2 receiver nodes in the 4x2 and the 2 transmit nodes in the 2x4 result in an overlap of these 2 plots. And then, of course, the 4x4 MIMO system outperforms the 4x2 and 2x4 by a factor of 2, and outperforms CISO by a factor of 4, as we expect for the linear increase given by the modified Shannon theorem. Okay, so let's move on to some current applications and challenges. This will include the Samsung Galaxy S5, MIMO and LTE, and some of the implementation challenges faced for the future of MIMO systems. So the Samsung Galaxy S5 was re-released in late 2014 in South Korea and was touted by Samsung as being the first cell phone to use single-user MIMO. Now it's important to note here that LTE systems currently use multi-user MIMO, and that'll be covered on the next slide. Now in the single-user MIMO system, there are multiple antennas on board this device. Because of the multiple antennas, the S5 can transmit or receive multiple streams of data on the LTE network all at once, which is the end goal of MIMO. And specifics are that it can either take in an 8x8 MIMO downlink or a 4x4 MIMO uplink. Now I'll talk about LTE systems and how they work with MIMO. The traditional cellular networks work best in line-of-sight conditions. Meanwhile, MIMO works very well in conditions with a lot of scattering. So in order to get the most out of MIMO, LTE networks need to be re-optimized for scattering conditions. Now this LTE optimization can be done without increasing the spectrum or number of base station nodes. Now this would not be the case if MISO was used to increase the throughput. So an analysis of the multipath conditions provides us with the transmission matrix that we discussed previously, so we can find the relationship between the receive and transmit nodes of the MIMO system. Additionally, the ability to reuse the existing equipment at the base stations while also giving an increase of throughput is important to the carriers, as that saves them money. As I mentioned on the previous slide, the Samsung SU MIMO, the LTE currently works with MU-MIMO, or multiple user MIMO. So this multi-user means that their mobile devices still have one antenna on each, but multiple devices share the space on the same channel from a single transmit node. Now the first iteration of widespread SU MIMO, which is where our large data rate speedups will start to come, is expected to be 2x2, which is the simplest implementation of MIMO, and should provide a 2 times increase in the data rate.